Dear students, today we'll discuss the significance of back EMF in DC motor and also we'll derive the torque equation in a DC machine. First we'll review once again the working principle of DC motor, how exactly DC motor works. That is, when current carrying conductor is placed under a magnetic field, there is a force is exerted on a conductor. Because of that, rotor start rotating. That is was studied in the last class. That is, it is demonstrated here. That is, you are passing a current to the stationary armature conductors, which is placed under a magnetic field. Because of current carrying conductor is placed under a magnetic field, there is a force exerted on a conductor. Because of that, the rotor start rotating. Therefore, the electrical energy inputted here, it is converted into mechanical energy in the form of rotation. That is observed here also. That is magnetic flux, and there is a current is flowing through these conductors. Current carrying conductor is placed on the magnetic field, force is exerted, the rotor start rotating. Then we look into the step by step how exactly there is a rotation is producing. Then what do you mean by back EMF in the motor? See, look into here, it is a stator system consisting of field N and S pole. These magnetic poles, they are producing a magnetic flux in between the N and S. In that magnetic field, we are placing the armature conductors. Then what we are doing, we are applying a DC voltage to the armature. Because of application of this voltage, the current start flowing in the armature conductors. Then we know that principle of operation, that is, there is a magnetic flux, there is a current carrying conductor is placed on the magnetic flux. Because of that, what happens? The rotor start rotating. The rotor start rotating. Just you have to pause it. Now, forget about the motoring action now. Now, what you are getting here is the conductors are rotating in the magnetic field. Rotor conductors are rotating in the magnetic field. Then, you can recall the generating action, that is Faraday's first law. Whenever the conductor cuts the magnetic flux, there is a induced voltage. You forget about the motoring action. Now what you have got? Because of application of the voltage, current is flowing. Because of the current is flowing in the armature conductor, which is placed under a magnetic field, the rotor conductor start rotating. Okay, that is the motoring action. Now the conductors are rotating here. Conductors are rotating. There is a magnetic field. Therefore, these rotor conductors are cutting the magnetic flux. Then, because of the conductors cutting the magnetic flux, there is a induced voltage in this conductor. There is a induced voltage in this conductor. The direction of this induced voltage is exactly opposite to the applied voltage. You can see here. Because of, if step by step you can once again recall, there is application of the voltage. Because of the application of the voltage, current is flowing. Current carrying conductor is placed on the magnetic field. The rotor conductor start rotating. Rotor conductors start rotating. Then, because of the conductors are rotating in the magnetic field, there is an induced voltage. That induced voltage is exactly opposite to the applied voltage. Therefore, this voltage is called as the back EMF. The direction of this EB is given by the Lenz's law. What Lenz's law states? That is, the direction of the induced voltage is very cause of producing it. What is the cause of producing EB? Producing the cause of ED is the rotation. How you are getting a rotation? Because of IA, which is flowing in the conductor, which is placed in the magnetic field. Then this current is because of what? This applied voltage. Therefore, the direction of the induced voltage is EB is exactly opposite to the applied voltage. That is, the direction of this induced voltage is exactly opposite to the applied voltage, because it is opposing very cause of producing it. Very cause of producing induced voltage is rotation. Rotation is because of IA. IA is because of the applied voltage. Therefore, this voltage is called as the back EMF. There is a induced voltage because of generating action in the motor. That voltage is exactly opposite to the applied voltage. Further, we can see here what we mean by the back EMF now. The first, I will start with the motoring action. The same thing I already explained. There is a field system producing the magnetic flux. DC supply is given to the armature conductors. Thereby, the current is start flowing in the armature conductors. Then, because current carrying conductor is placed under a magnetic field, therefore current is start flowing in the armature conductors. Because of the motoring action, the force is exerted on the armature conductor. Thereby, the armature start rotating. It is a motoring action, step by step. After this, you can observe here carefully. That is, after motoring action, there is generating action starts in the motor itself. Now, where it is motoring action stops here, the rotor conductors are rotating. Okay, I'll start with that. The armature start rotating, thereby armature conductors also rotating. These rotating armature conductors are cutting the magnetic field. There is a field system in this system. Therefore, these armature conductors are cutting the magnetic flux here. Thereby, there is a voltage is induced in the armature conductors. The direction of this induced voltage is given by Lenz's law. This voltage is called as the back EMF of the motor. That is, the EMF which is induced in the armature conductors because of the conductors are rotating after the motoring action. It is cutting the magnetic flux. There is a induced voltage. That induced voltage is exactly opposing the applied voltage. Therefore, it is called as the back EMF. Then we will continue with the back EMF here. You can see here. There is a flux because the current is flowing through the armature conductor. What you are getting? There is a rotation. You can observe here carefully. Rotation. Because of this rotation, conductors are rotating in the magnetic field. There is an induced voltage. That induced voltage is what we are calling is the back EMF. That is EMF which is opposing the applied voltage. Therefore, it is written once again the same thing. When the armature of the DC motor rotates under the influence of the driving torque, the armature conductors move through the magnetic field and hence EMF is induced in them. As in a case of generator, the induced EMF act in the opposite direction of the applied voltage V. It is given by the Lenz's law and is known as back EMF or the counter EMF. Then, what is the magnitude of induced voltage? The magnitude of this induced voltage EB is depending upon the strength of the magnetic field, the speed of the rotor, the number of poles, the number of parallel paths, same as the generator equation, but it is represented by EB. That is, the back EMF EB is given by, it is depending upon the flux strength, it is a number of conductors and the speed of the rotor as well as the number of poles and the number of parallel paths. It is same as generated voltage, but the direction of the induced voltage, it is because of the motoring action you are getting the voltage here. That voltage is exactly opposite to the applied voltage. Therefore, it is called as the back EMF. Therefore, the EB is given by 5 ZNP by 60 into A. Then if you are representing this with a circuit model here, in this case, you are seeing here, you are applying the voltage here. to the armature, there is a current is IA, then there is a voltage is developed which is exactly opposite to the applied voltage. Exactly opposite to the applied voltage. Therefore, you have to establish the relation between V and EB. Suppose I am drawing the equivalent circuit of this, the motor. That is, V is as it is here, then EB is represented by source of voltage. Then we know that there is a drop in the armature because of the armature reaction, the brush drop and the commutator brush drop as well as the armature reaction drops are neglected for simplicity. Therefore, I am representing this armature by a back EMF EB which is exactly opposite to the applied voltage, and there is a resistance RA, then the current is I. Therefore, how we are establishing the relation between V and EB? Just have to apply the KVL for this closed circuit. That is, V is equal to EB plus IRA. The current which is flowing through the resistance is IA. Therefore, that is, you can apply the KVL here. V is equal to EB plus IR. Therefore, applied voltage V is equal to EB plus IR. In other words, the back EMF EB is equal to V minus IRA volts. You can transfer this IA to the left hand side. What we are getting is V minus IRA volts. From this relation, suppose I am interested in the armature current I, that is V minus EB divided by RA amperes. This is the relation for the armature current in the motor. V is the applied voltage, EB is the back EMF, I is the armature current, RA is the armature resistance. You can observe here the one more thing. The back EMF of this machine is given by this equation 5ZNP by 60 into A. Then you have to see what is the significance of the back EMF. That we can observe here. The back EMF, you have concentrate on this equation. Okay, then also this equation at the same time. These two equations you can observe here. At the time of starting, what is the speed of the armature? The speed of the armature is 0. That is, N is equal to 0. If N is equal to 0, then what is the back EMF? The back EMF is also 0. You are putting the value of N is equal to 0. Therefore, back EMF is 0. Then you look into this IA equation. IA is equal to V minus EB by RA. If it is at the time of starting, the N is 0, thereby EB is 0. Therefore, the IA is given by V by RA. V by RA. RA is very small. It is in terms of 0.1 or 0.2. The applied voltage is around 220 and more. In that case, what current you are getting? 220 divided by 0.1. You can call it as 2000 amperes you are getting. 2000 amperes of a current getting. Means very high current it is drawing at the time of starting. The DC motor always draw heavy current at the time of starting because the back EMF in the machine is 0. Because of that, then what we are getting is the current is very high. Therefore, to start with the DC motor, you have to apply a smaller voltage or you have to go for a starter to minimize the initial inrush current. That is the first observation. That is, when at the time of starting N is equal to 0, EB is equal to 0. Thereby, if you are looking into the current equation, in the current equation EB is 0, IA is very high. Therefore, you have to make use of a starter here. That is the first observation. Under running condition, what is the speed? Speed is almost equal to its rated speed. It is nearer to its rated speed. In that case, the back EMF EB is almost equal to the applied voltage. That is, under running condition, speed of the machine is nearer to its rated speed. Thereby, the back EMF in the machine is almost equal to the applied voltage. It is not equal to the applied voltage. It is nearer to the applied voltage V. Thereby, if you look into the current equation here, in that case, it is drawing a lesser current. Under running condition, V minus EB divided by RA. EB is almost, suppose if it is applied voltage is 220, then in that case the back EMF is around 218 or 215. So that the difference between V and EB is very small, thereby the current is well within the rated value. It is well within the rated value. You are seeing the two observation. When speed is equal to 0, then the speed is the rated. Then what is the loading effect and what is the effect on the speed because of the back EMF? That is also you can see here. That is, when the load of the machine is increasing, what do you mean by the load? You are extracting more and more the mechanical power from the motor. If the load is increased, the current drawn is also increasing, because as the load increases, the current has to increase. Okay, however, the applied voltage is constant. That is what you are observing. When the load on the machine is increasing, the armature current is increasing. Because the armature current is increasing, then you can observe this formula. That is, if IA is increasing, then what happens? IARA is also increasing. IARA is also increasing. Means, what happens to the back EMF? The back EMF is decreasing. As the load increases, current increases, IARA drop increases. Because the IARA drop is increases, means it is a difference between V minus IARA. The difference goes on decreasing, thereby the back EMF is decreasing. If the back EMF is decreasing, then what happens? See here, flux is constant, Z is constant, P is constant, 60 is constant, and A is also constant in the DC motor. If the back EMF is decreasing, it is directly affecting the speed of the machine. Means, as the back EMF increases, the speed is also decreases. This is how you have to analyze the equation of the back EMF. In the next class, we will discuss the derivation of, we will derive the equation for the torque equation.